When we create and implement web service applications with the Spring framework, we usually have lots of different concerns. One of them is which design pattern are we willing to use? Normally, we use the MVC design pattern, which is short for Model View Controller. And then we define our payloads, which also are usually in the format of JSON. Then we implement our controllers, our services, our business layer with them, and then we implement our data access objects, our DAOs, which then we make them using repositories. And these repositories come from Spring Data. And then we return our requests, our responses, and then we could give the callback to the client. And using the MVC design pattern is a blocking way to do things. So that means that sometimes it's also important to think if we want to have a reactive application. And that's when we start looking at other alternatives that the Spring framework also has to offer, which is WebFlux, for example. And then we can choose coroutines perhaps on top of them. And the idea is to make the application more resilient. And this is a concern to make sure that our Spring Boot application can process more requests at one given time. But not very often we worry about another variable of our services, and that is the startup time. It is important to think about it, but not in all scenarios, just as much as reactive is not important for all scenarios. Sometimes we really need to use the easiest solution that may not be the most efficient one, but perhaps is the one that gives us a better alternative. But let's go back to startup times. We have seen in this channel 2 other videos. One was about GraalVM and another one was about Project CRAC, C-R-A-C, which also means Coordinated Restore at Checkpoint. These 2 projects were concerned about one single aspect, at least the most important one, and that was the startup time. And the way GraalVM does that is by compiling our application to the native code. So that means that one thing that it avoids by doing that is simply it compiles natively and it starts the service natively, which means that we can avoid just-in-time compilation problems or how long it takes just by doing that. When we look at CRAC, one thing that it does is it allows us to start our application, see where's the checkpoint that we need to create, and then we create the checkpoint from that moment where we see that our application has a certain stability that we are interested in. But there are drawbacks to both of them. On the one hand, GraalVM takes a lot of time to compile. We really take a long time before we can actually deploy our application or finish deploying the application because it takes so long to compile, which means that the round trips to perform a deploy are quite long with GraalVM. Project CRAC, on the other hand, has another issue, and that is that we are the ones to decide when the checkpoint occurs. So when we say that our application will start from that point onwards, that is our decision. That is not CRAC's decision. And so these 2 solutions, although they answer the problem of startup times, they carry with them some issues. But there is one alternative that is also often overlooked, and that is Spring CDS, which means Spring Class Data Sharing. So let's get into it. Start from the package, Spring CDS Class Data Sharing by João Esperancinha, and the date that you see over here on this slide is the 19th of November 2024. This isn't the date of this video, this is the date where I finalized the slides for this presentation. But before we continue, a bit about me. So my name is João Esperancinha, my pronouns are he, him, his, And I have been working in different technologies throughout the years, namely Java, Kotlin, Groovy, and Scala, for more than 10 years as a software engineer. I am the owner of the JustProtect YouTube channel, JustProtect Software Engineering, and to the right you can see my credentials. I am a VMware Spring Professional 2021. I am a Java SE11 certified developer of 2019. I am a Kong champion, and of course I am the owner of this channel. In today's agenda, we are having a look at different topics surrounding class data sharing, namely with Spring. The first topic is the problem. We are discussing why should we need CDS and what are we trying to solve. Then we are also having a look at the different solutions that we can pick to solve the problem that CDS also tries to solve. We are talking a bit of the history of CDS. We are discussing, of course, what is class data sharing, how the JVM works with CDS, what are the benefits of using CDS in Spring applications. Then we will learn how to configure CDS in Spring projects. Then we will talk about real-world use cases and benchmarks and how to create a benchmark to make performance tests. And then finally, we will have a quick talk about best practices when applying CDS and using CDS for our Spring applications. This is our agenda for today. We are going through all of these topics through the course of this video. And the idea is to understand what CDS actually is, what class data sharing can do for us, where to apply it, where it's being used today, and what can we learn from it. But we also need to understand what CDS is not, because there are a ton of misconceptions out there, and I want to talk about 4 of them at this point. One of the big misconceptions about CDS is this one over here. And this one tells us that CDS came out with the release of the Java JDK 1.5 and that it was found on it. It says that it was discovered and that nobody really understands how to use it and what was it for. And that at the time, people didn't use it because it wasn't official. This is a bit of a myth, and it is not true. CDS was deliberately created by Sun Microsystems with the idea of making applications start faster and to not have to restart the process of class loading, namely, but also the parsing, the verification process that it entails, and everything that is needed to just get our application to start. So it was not found, it was not a mistake, it was not something that came unexpectedly in the release. It was created specifically for this purpose. It just didn't took off and not many people were interested in it. The second misconception is this one over here, which tells us something interesting about the class loader. This one is not specifically related to CDS, but it may pop up when discussing CDS. And what it tells us is that the class loader creates classes. And at that point, you have to stop the conversation because CDS does not create classes. So the class loader does not create classes. Runtime uses that, and it uses the class loader to load those classes, and then it parses them, and then it verifies it, and then it uses the metadata, and then it runs the application with all of the other multiple different processes that occur in between. But what it doesn't do is create classes. The class data loader loads classes. It doesn't create them. The misconception number 3 is this one over here. And this one over here tells us that class data sharing works like a cache, and sometimes it is a cache. The reason for this is because when we use class data sharing, we create a file, namely one file that it's called the Java Shared Archive, the JSA file, that contains all of the data that is necessary when we start our application. As I mentioned before, metadata, verification, the parsed classes, all of that thing that gets generated in memory goes to that file. And people tend to think that that file is a cache. Let's look at the definition of what a cache actually is. This is it. And important to note is that a cache is always available in the runtime of the application. We can access different properties, frequently with keys, and we can use the cache as we want, and we can perform mutations on it. And what that allows us is an easy access to data when the application is running, during the application runtime. But that is what a cache is. The JSA file gets loaded only once when we start the application. The application starts, it does everything it has to do during startup, and that's it. Then we don't use it again. We don't change it, we don't mutate it, we don't access it again. So it doesn't fall into definition of what a cache actually is. And therefore, it is not a cache. Misconception number 4. This is the last one. And the misconception number 4 tries to make a comparison between how GraalVM works and C and C++. So what it says basically is that GraalVM, being an alternative or a potential alternative to CDS, what it does, it can compile a Spring Boot application or in general a Java application, and with it create the matching code, the matching binary code that can run natively, which means regardless of the JVM, which means that it does not need a JVM to run. It is a completely independent file in the end. GraalVM has that disadvantage that we should know at this point, and if you don't know it, that's not a problem as well. Essentially, it takes a long time to compile. When I mean with a long time, I mean a really long time to compile. Minutes, 10 minutes sometimes. It depends on the application and what the application actually does. But the point is, at the end, you do get a file. You do get an executable that can run in your machine natively, and it will start very fast, in seconds sometimes, in less than a second sometimes, in milliseconds sometimes. And that is valid for complicated applications or simple applications. And the reason for that is that it applies ahead of time compilation, which means that it doesn't perform just-in-time compilation, and that means that our application can start very quickly with GraalVM. But what comes out of these discussions sometimes is a comparison of GraalVM and the native images that we can create with them, and also the commands that we can create with it, with code that the binary code that is compiled with C or C++, and frequently directly referencing C++. The problem with that is that C, C++, and the results of GraalVM, they all compete in the same league. To make a comparison between GraalVM and the binary code that results from compiling source code created in C++ or in C, it's basically comparing a blue light with a blue light, a green light with a green light, comparing apples with apples. it doesn't make any sense to say that GraalVM can be potentially faster than native code in C++ or C, because it doesn't make any sense to make that comparison. Alright, so these are 4 different misconceptions that should now prepare you for the rest of the presentation. So now let's discuss the 3 different options that are available to make our application start faster, and just briefly go through it again and talk a bit about them in the slides. So what problems do we face today? Of course, we are facing startup times issues, and it affects a lot of areas of our development environment. One of them is auto-scaling, of course, because if we want to change the characteristics of a database, for example, or if we want to raise our memory available, then that sometimes means restarting our machines, and restart also means startup times. The other thing is, of course, deployment times. If we have a continuous delivery system implemented, then the likelihood that it will take longer to deploy due to the startup time of the applications is very high. And in the same way, we are dealing with constant initializations all the time. When it comes to services, we may need to configure some properties, the port where they connect to, the database where they connect to, perhaps the database selves, or something like schema, whatever. It may need reconfiguring, and sometimes you cannot do a live configuring of these services, and therefore you need to restart them. And that, of course, at the cost of the restart time. But the solution that we are talking about, of course, is Spring CDS, which has a promise to save these problems. It comes with caveats, but it comes also with a lot of benefits. And there are also 2 solutions actually that we can choose from, and one of them is GraalVM. And as mentioned before, GraalVM is based on a virtual machine. It uses hotspot, and it has the ability to create virtual images. And it has also the ability to create native images. And with that, we can create runtime applications that are fully independent of the virtual machine, and they can run in your local environment via, for example, the command line. And that means that they will start much quicker. They have included an ahead-of-time compilation, which means that the just-in-time compiling process that frequently virtual machine dependent applications need to go through is not there, and therefore they usually start up at record times. There is a small problem in the meantime, is that the iterations that we need to perform normally in development to create applications is much longer, because the compile times are hugely higher than the normal compile times of a simple application. With that said, we could also look to other alternatives, like, for example, coordinated restore at checkpoint, otherwise known as Project Crack in Spring. And Crack has the great ability to let us start the application and then choose where and when we can create a checkpoint so that we can restart our application from that point all the time. It can be a cumbersome process, and the idea here is that we are able to restart the application from that point onwards. So, for example, if we start our application, we need to establish connections, and we need to have something in memory, like, for example, a cache. The likelihood that the cache will be restored is very high, but the restore of the database connections will depend on how those connections are implemented. And in many cases, the connections aren't restored, they need to restart as well. So Crack is also not a 100% reliable solution, precisely because we need to be aware of that when we create a checkpoint, which essentially is a folder with a lot of different files that save the state of our application, it won't necessarily save everything. So it won't start the application immediately. That is a property that GraalVM can offer very well. But as an extra alternative, we've got, of course, CDS, class data sharing, which is also compatible with Spring now, and Spring leverages the process of creating a class data sharing archive, which is the Java sharing archive or Java shared archive that we can find in our folder once we start an application with this class data sharing activated. But when and how CDS started, we have to look back at a while ago, and that's a very long time ago, because it started with Java 1.5, and Java 1.5 was released in 2004, so it's quite long ago. And just to get an idea of the time frame, that was the year that Franz Ferdinand released their first debut album. That's when Green Day released American Idiot. That's when we saw the release of Eternal Sunshine of the Spotless Mind with Jim Carrey and the movie Day After Tomorrow. So that was a long time ago. In 2018, CDS evolved to allow application class data sharing. And what this means in short, and we will see that later in the presentation, is that the file that is created, that is our data sharing class, also was able at this point to add classes specific to our application and not just the JVM. And to get an idea of what happened at that point, Ariana Grande released this album, that's Florence and the Machine, and Red Sparrow the movie was released. In 2021, dynamic CDS archiving was available, and it was available also with Spring Boot. And this just means that we could restart our applications, and our class data sharing archive was now able to refresh itself and create a new one, which is very handy and useful when we are developing applications. Now, this was the year of this album by Billie Eilish, the other one from Taylor Swift, and the release of the movie The Guilty. And this is a short time frame of when and how CDS has started. So there is a long evolution of about more than 2 decades in the making of this way of starting applications. But what is class data sharing? Now, we have just looked at a few interesting aspects of CDS, and you may get the feeling that it's maybe complicated. It's not, I promise. It's very easy to program and make an application run with CDS. But what's important at this point is to think about what we have just learned. The important thing is we now know that we need to create a file and that the service starts from that file. That file is not a cache. We also know that in that file, there's all the information needed to start our service. So we can get our service just at that point where everything gets started. And that, of course, will accelerate the startup process. Another thing we know is that it took a few decades to get CDS available, and also now available and fully compatible with Spring, which leverages that process. But perhaps one question remains, and it is, what is class data sharing? What does that entail, and what does that mean to do that? So, let's go back to our slides. We have discussed what class data sharing is. We have learned a bit how is it created. But there is an added point to it. So CDS is a JVM feature that allows sharing of preloaded class metadata among multiple JVMs, reducing startup time and memory footprint. The new added point here is that we can share it between different applications. So that means that one JSA file doesn't need to serve one specific application as long as the classes that are shared are the same. Class data sharing is enabled by default in modern JDKs. What this means is that one JDK will have a JSA file in its folders. If we look at the directory structure of one JDK, we will find JSA files in there. This is something that we will see further ahead in this video, and we will realize that all versions from version 12 will have JSA files in them. The class metadata, as we have seen before, is stored in a shared archive file, a JSA file, which means Java Shared Archive. There are two types of class data sharing. One of them is a shared archive with default JDK classes. This is the file that we typically find in new JDK versions from version 12 onwards. And we can also find appCDS. So these means that these are application-specific class data sharing files where custom classes are used in specific applications. So these are application-specific classes or the setup of the classes before the application starts. So what is the JVM and the CDS performance like? We have just seen two different types of class data sharing. And with this, we kind of know the basics of how it works. We now know what it is, how it works in the background, and what we are supposed to achieve. But what we still don't know is what do we have to do to activate all of this? Because the theory, that's something we've got. So we're good there. But we need to know how to start this. We will see this now, but before we continue, it's important to understand that whether we ever choose GraalVM or Project Crack for Spring, or CDS is completely up to our understanding of how these frameworks work and which specific use case do we have. And bearing that in mind, let's now see how CDS can work for us via, in the first instance, command line arguments using the Java command line tool. So let's get into it. The JVM and CDS have an influence on each other in terms of performance and how the application behaves. We have seen before that JVM skips loading classes into memory by reusing preloaded data that is available in the JSA files, the Java Shared Archive files. It reduces the just-in-time compilation overhead during startup. This reduction in the just-in-time compilation is really specific only to startup. When it comes to the runtime just-in-time compilation that also occurs while we are using the application, CDS has no effect on it, because CDS only affects the startup of the application when it comes to things like data loading and the data class loading. With CDS, multiple JVMs can share the same metadata archive. As we have seen before, this is a reality that is important for different applications to run because we can map directly the startup of certain applications if they share the same classes, and therefore multiple JVMs will be able to start much more quicker. The more JVMs we have that depend on the same JSA file, the quicker our startup will be, and it will be quicker in an exponential way. It will decrease the memory usage on systems running multiple JVM processes, and the reason being is because it doesn't need to load so much in memory when we are starting with the JSA files. It has a faster context and dependency injection processing. This is normal because if we are saving every single optimization that happens during startup and we are placing that in a specific file that contains that, then of course some of the injection processing will be already available when we start the application. And what are the benefits of using CDS in Spring applications? As you probably know already, it will provide a faster application startup for microservices and serverless functions. The reason for it, of course, we have seen before, is the class loading that gets much faster just because everything is saved on that file. And for serverless, it's also the same case because they are serverless functions, but they may use Java applications just as well. And that means that the startup can also be improved by using CDS. CDS implies that we are using much less memory on resource-constrained environments like, for example, Kubernetes. What this means, of course, is the same thing as we have mentioned before. There will be less usage of resources simply because we only need to map our JSA file to memory. CDS also supports efficient scaling of Spring applications with multiple JVM instances. This is the same and just reiterating what was said before in the previous slide. How to configure CDS in Spring projects. CDS is already pre-configured in JDK. And that means that from Java 12 onwards, from 2019, it is already possible. Not only it is possible to use CDS, but CDS is already in use. And if you have been using a JDK at this point with a Java version that is higher than 12, you have been using CDS without even knowing it, because it's there and it is available. 2019 was the year of the release of the album of Billie Eilish. It was a release of one album of Harry Styles as in there, and there was the release of The Good Liar. So it was a while ago, a couple of years ago. In order to be able to start an application with CDS enabled, and particularly a CDS that is optimized for our Spring Boot application, we need to use this switch over here, -x share on, to explicitly enable CDS in Spring Boot applications. To be able to dump the class list to a file, we will need to use the flag -xx dump loaded class list to generate a class list. And then, to be able to create a shared archive file, we can use this flag -xx shared archive file and then define the path where it is located to be able to store or load the shared archive. This was just a short overview of simple commands that can activate CDS for us and can allow us to use CDS. But CDS is a vast world in itself, and there are a lot of different commands that we can also use with it. We will see how to use this in simple Java applications, but also with Spring applications. We will also see how can we verify that CDS is actually being used and what is the difference between an application that does not use CDS and another one that does. And to understand these principles, nothing better than a demo right over here. On GitHub, I have a project called Spring Master Test Drives. And in this project, we can find different modules and they serve different purposes. But there are two that are of our interest for this video. One is the validation company, and the other one is the validation company Simple CDS. The first one is a Spring Boot application, and the second one is a simple Java application. And the idea here is to see the behavior of the two different applications and find out what are the differences in each case between starting them with CDS and without CDS in a different order. So first we are starting our applications without CDS, and then we are going to compare that with an application running with CDS. If we go inside of the first case, which is the simple CDS, we can see then that we've got one makefile, and in this makefile, everything is done for us. What I mean with that is that here we've got all our scripts and all our different commands summed up into small makefile commands so that it's easier for us to run this and to get an idea of what we are doing. So if we start from the top, we can see that there are these commands to create the wrapper, to clean the application before we start, to build it. Then here it's important to know these flags. The first one allows us to check options in the JVM, like memory, when we are starting the application. This is of our interest when we are starting it. Then we need to get an information about the memory tracking information. This is because we want to know how much memory is being allocated for the different classes that we are loading in a class loader. We also want to know the startup times, and then we log, of course, the startup time of our application. And then at the end, of course, this should be already known to you if you are a Java developer or have worked in any case with a JVM. And if not, it is simply a command that says to run a jar file in the JVM. And there's a -- keep here. We'll get to that in a minute, but let's first go through all the other commands. Right over here, we've got this command verify CDS, which basically does a find in the SDK-man folder where all the different SDKs are stored. If you know, SDK-man is a SDK manager, and it allows us to download all the different SDKs that we need. In this case, it will just look for all the different folders inside of it. So all the different SDKs that I have installed locally. I believe I have SDK 13, 14, and so on, up to the SDK 21 of Java. Then we've got the series of commands needed to work with CDS. The first is the extract. And I can say firsthand that this one, we will have a look at it, but it plays no role in starting the application. I just want to prove a point in a while. Then we've got the CDS class list. This creates a list of all the classes that we need in our application to start. This is important because then we want to create our JSA file, our Java Shared Archive file, with the class list. Then we can launch our application with this flag over here, share on. We'll also manage the startup time. We will start our application with our JSA file. Again, the same options to get the information about the memory usage. And then, of course, the jar with the keep flag. And so on. There are different commands as well. The launch logs, it means that we can log every single information about the service when it's starting up, and also during usage. And here we've got a different list of commands that allows us to check what is going on inside our running jar in the virtual machine. And it's just a simple list of commands that are not directly related to CDS, but are commands that we can use with the jcommand utility, which is also called a Java command utility. Earlier in the video, we discussed two different types of CDS. Just CDS, class data sharing, and application CDS, app CDS, or application class data sharing. Now it's a great moment to see the difference, a very clear difference between one and the other. And for that, let's recap a few things that we discussed before. A very simple thing is that CDS has been available by default since version 12. It started in version 1.5. How we activated CDS between versions 1.5 and version 12 are less interesting for this video, because we are already on Java version 21. So the JDK has evolved a lot, and that means that we have a much more evolved software development kit. But it's good to see exactly what it means to say that we've got CDS by default in modern JDK versions. So let's run the verify CDS command in the make file, which essentially looks for a file called classes.jsa in the folder of SDK-mon. Let's see what happens. If I run make, just put this a bit bigger for us to see. If I go to folder the validation company simple CDS, and then I run verify, then I get a list of everywhere where we can find classes.jsa. And if we take a good look at what we have here, is that all the versions that I have installed do contain a classes.jsa file. And we can see over here Java version 20, 18, 16, 21, 12. In no version earlier than 12 we can find a classes.jsa. Another 19 version, 17 version, then there's a crack version and a GraalVM version, and all of them have classes.jsa in them. And if we do just a quick listing of the folder that contains all of these JDKs, the SDK-mon folder, and we go to candidates, and then we go to Java, I believe, then we've got all the versions over there. And we can see that I still have a version 8 and a version 11. And in none of these versions could we find a classes.jsa file. We can go even further and see if version 11 contains a classes.jsa file in its lib folder and in its server folder. All that we can find are SO files and a text file. That's it. But there's no classes.jsa file. It means that these versions under version 12 do not have a Java shared archive file. But the Java shared archive file for the JDK is only related to the JDK classes. We need specific classes for our application, and those are taken into account when we create our own application.jsa file. So let's do that now. So if we go to our make file, we can find different commands that are related to CDS. The first command on the list is CDS extract. This CDS extract is run with the Java command and then with the flag -d, jar mode tools -jar, and then the name of the jar and the extract. What this command does in a Spring Boot application is extract the jar file, and it creates a new jar file that we can then apply CDS to it. We will see that later in our Spring Boot application, but this doesn't work in a simple application because we can apply CDS directly to our jar, to the jar that we will create here. Before we activate CDS in our application, it is important to understand our application a bit more. And for that, let's first go to main to see what it does. If we go to main, we see that the main method is this one over here. And the first thing it does, it prints out hello and welcome to the console. Then it will print out a series of 1 to 5 numbers to the console, and at the end it will test if we do have a flag called --keep, and if we do have that, it will sleep for 1 hour. This is important for a few commands that we will issue further down this video, but for now we get a good idea of how this application works, and let's see how is this packaged. So let's look at the build Gradle KTS file, and from here we can see that we are creating a jar, that is a runnable jar that will depend on this main file and will run from here. This is how we then create the manifest, and then we just simply run the code that will be compiled in this folder over here. The rest of the commands are needed for other aspects of the build, but for now they are not of our interest for this video. So let's now go back to the make file and let me explain how does the first step in activating CDS in our application works. We first need to create a list of all the different classes that are needed to run the application. And to do that, we simply issue Java with this switch -x share off, and this means that the application will run without the ability to share the class loading between different applications that use the same classes. Then we create a list of all of these classes with this switch over here, -xx dump loaded class list. And we will dump this list into this file over here. Next, we issue this -cp, and then we use the location of our jar to indicate to Java that it will need to build the list of all of the classes from this jar and dump them into this other file, classlist.txt. And at the end, we indicate simply the main class where the main method is located. Main class in this case in Kotlin means the object main where the main function is located. Before we can start this command, we still need to build our application. And for that, we can just call make, because make from the beginning calls this B, and this B calls the wrapper, it cleans and it builds the application. So if we wait until it's done, it shouldn't take too long. It will now build, yes, so it has already built our jar, and so now we can just call this command here, which is a shortcut to the whole command that I've just mentioned. So if we call make CDS class list, it starts the application literally, and it creates the class list that we need. This is our class list, and we can open it in IntelliJ, and if we go from top to bottom, we see that it contains a lot of classes from the JDK. And at some point, we should be able to find our class, because remember, this is a list of all the classes, the CDS classes and the application CDS classes. If we try to find org/singer, there, we see that the main class is also taken into account in this class list. With this class list, we can then build our first JSA file. Remember, it's called Java shared archive. So our Java shared archive is created using a slightly different command. In this case, we start with -share dump. This already indicates that we are creating a dump file, in this case a Java shared archive. We mention the location of our class list file, which we do via this switch -xx shared class list file. Next, we have another switch, which is -xx shared archive file, and this is the file we are creating, our JSA file. We call it application.jsa. And at the end, we simply hand in the location of the jar file that we are using. So let's create our JSA file. And in this case, we just need to call make CDS archive. And when we do that, we should find at the root of our module the application.jsa file. We could open this file, but it's filled with binary and other kinds of code. We cannot really read it. I can probably show a bit of it if I just perform this command. If I just issue cat application JSA, see, we have a lot of binary and different kind of code, and this is not readable. But this is where the information of the start of our application is saved. And this has the class loading information, the different kind of stuff that is needed for our application to start, all in one single package. The way this works when we launch the application, which is in the third command, is that the application will start with what we saw before. So if we call verify CDS command, we see that we've got the classes.jsa located in the different JDKs. It loads this classes.jsa and it loads the application.jsa. And to be able to launch it, we of course need to launch it with a different kind of switches. And in this case, the first thing we do is share on, which means that we can share our classes via this application.jsa. Then we also activate the logs. This is important so that we can register and measure our startup time for our application. Then we issue another switch, which is the shared archive file, which is the same switch as we have done before. The only thing is that now we have the share on activated. So instead of dumping, we are activating it and we are using it. We are actually now activating CDS for our application. We have two more switches which are important to be able to access important information about the memory allocation in our application. This is for diagnostic functions and this one is for the native memory tracking, where we will get the summary of the memory that we are interested in seeing and measuring. At the end, we simply call the -jar. If you are not familiar with it, the -jar simply loads the jar file into the Java virtual machine. And in this case, we do activate the keep flag so that we can have the application running for enough time so that we can perform other different checkups. This is how we launch an application with CDS activated. We want to see the difference between applications that start without CDS and the ones that start with CDS activated. And in this case, we are specifically talking about application CDS. To calculate and see that difference, and to understand and compare the different results, I have created a table for it that we are going to fill in the course of this video. The table is located on the README MD file in the validation company Simple CDS folder. That is the root of this module. And right over here at the top, there are different things to look at. On the left-hand side, we've got the properties that we need to measure, and then the two different applications that we are investigating. The first column is our Java application, the one that we are looking at this point, and then we've got the Spring application that we will see later. We will measure startup times with and without CDS. In this case, first without CDS and then with CDS. The committed memory without CDS and with CDS, and the total classes loaded without CDS and with CDS. The idea is that then we've got a lot of results where we can take some conclusions about it. Let's go back to the make file. And first, let's run our application without CDS. But we will launch it with a couple of flags that we needed. The first one is the unlock diagnostic VM options, as we have seen before. Then we've got the native memory tracking, which is important that we get the summary of it. And then we log the startup time. And of course, we are starting the application with the keep flag so that the application stays running for at least 1 hour or until we stop it ourselves, which is what will happen. This is the run command. We are already inside the correct folder, so we just have to do a make run and our application is already running. And we know already that our application took 23.11 milliseconds to start. So let's put that in our table. Right over here, without CDS, it took 23.11 milliseconds. Now let's see what happens with the committed memory. And for that, we can go here to our makefile and go all the way down to verify. And in these verify commands, there are different commands that we can run to check the status of our running application. The ones that we are interested in are the class loader stats and the native memory summary. The other commands we can have a look at, or you can have a look at in this case. We won't investigate them because they turned out not to be very interesting to investigate the effects of CDS. They do provide extra information, but not visible enough so that we can understand what CDS is doing. In our table, we are missing two fields now that the application is running. One is the committed memory, and the other one is total classes. For the committed memory, let's first go to the native memory summary. And for that, we will open a new tab and we'll go to the CDS folder, and there we can start the CDS-verify native memory and check on the results. Over here we've got a lot of different things: metaspace, serviceability, synchronization, SafePoint, module, and so on. But what we are interested in is the shared class space, where we see that the committed memory is 12 megabytes. So let's put in our table 12.952 megabytes. Let me change also the units here. These ones don't even have a unit, the total. This one's going to go, and now we're there. So the committed memory without CDS for a Java application in this case is 12.952 megabytes. Now we need the total classes, and for that we've got another command, and that is the class loader stats. If we call make CDS verify class loading, then we see all of this information, and we see that the loaded classes in this case is 815. So let's put the 815 in our table. Go over here, without CDS, 815 classes loaded. All right, so this is the statistics for our Java application without CDS. Let's see what happens with CDS. And for that, we stop the application and then we just do a make, as we have seen before, launch, and it's just a CDS launch. So now we've got our application started. In the other tab, we can now run the same commands. But the first thing we want to pay attention to is, of course, the startup time. And over here, we can see that the startup time was 29.27 milliseconds. Let's pick that up and throw that into our table. And this would be with CDS. And now, if we put this one here, we already see a weird difference. So without CDS appeared to be faster than with CDS. We can ignore this for this moment because the difference is actually only 3 milliseconds between them, and that is pretty negligible at this point. Okay, so for this simple application, being faster in startup didn't really work. Let's see other characteristics. Going back to our makefile and going back to our Java commands, let's see. The first one that we can start is the memory summary, and for that, let's do a make CDS verify native memory. All right, so now it has launched the command. It sends us a lot of information about memory just as before, and we can see that the committed memory is now right about 8 megabytes. So let's copy this and put that in our table. Over here we've got the result, and now our committed memory has been significantly reduced. And because we have a relatively small application, but now only 8 megabytes are needed. That is a 3 megabyte difference. Megabytes is not a lot these days, but it is a lot considering how small this application is. Would the total classes be different? Let's see that as well. And for that, we already know kind of how the command looks like. That is using the make cds verify class loading, which will issue this command here, vm class loader stats. And in it, we see actually an increase in classes, because now we have 818 classes. And if we go back to our table, we actually only see one improvement for small Java applications, and that is the memory footprint. It's lower with CDS than without CDS. For the other ones, we can't really make much of an assessment because the results are so similar to each other. But we are definitely sure that the amount of memory needed in the second case with CDS is much lower. So this is the analysis for a simple Java application. Doesn't seem much, but let's have a look now at something that could potentially be more different, and that is with Spring. And right here I have the original, the validation company application, which is a Spring application, which is far more complex than a simple Java application. And for that, let's first have a look at how it is built and which libraries it uses. If we go to buildgradle.kts, we can see that it uses the Spring dependencies, the Spring Boot Starter, Spring Boot Starter Web, Spring Boot Starter Validation. It uses the Kotlin Reflect library, and it also uses other things like for tests, it uses the Spring Boot Starter test, it uses the JVM runtime for Kotlin, and it also uses JUnit. Here is the important part. It uses other external libraries. So it will create a fairly complexer jar than the one we saw before. Let's go through the code for a bit and see how complicated can this application actually be. It is an application that has DTOs, and that means it has a layer facing the front end. It has a REST controller. It has got assertions here. It has got other kinds of DTOs. It uses configuration files. Let's see what this one has. It's got a bean, a validator bean, and it has validation fields. So it is an application that uses different kinds of libraries in different kinds of packages. Therefore, it's slightly more complicated. This project also has a makefile. So let's first look into that. The makefile is located at the root of the project, right over here. And here we can see a similar file to what we saw before, but with the command specifically designed and tailored to the Spring Boot application that we have over here. At the top, we find common commands. How do we start the application? And of course, the different extract commands. And we do have a substantial difference here than with a simple Java application. For Spring, when we create a Spring application, we are packaging classes, but we are also packaging jars. Together, they make our Spring Boot application. But this is something that CDS for applications, that is app CDS, cannot act upon. It needs to act on the unpackaged application. And for that, we need first to extract it. This is the command that I said before that it's not interesting for a simple Java application, purely because that Java application is a simple package of a simple set of instructions in Java that do not need external libraries. The following steps are related to how we activate CDS in our applications. But I have changed our table in the meantime, because we want to measure other things with the Spring Boot application, because there are more possibilities. So let's look into that. In the README file, we can see that I have added at least 2 more extra measurement types for the Spring Boot application. And what we find here is that there is an extra option for unpacked runtimes. So this means that we are going to extract the Spring Boot application and run from there. And that has a startup time just as much as the simple normal jar package that we are used to using for Spring Boot applications. And there is an extra option, which is this AOT option. This means ahead of time. And this means that if we activate this, we, in a way, limit our application into what we can use with it, but we get the benefit of providing, during compilation time, some optimizations that are usually only made with just-in-time compilations. That means that the application is already started, and there are usually extra optimizations made to the running code, so that the Spring Boot application only performs them when they are actually needed. And this saves normally startup times. But we can do that also if we activate this option, which is the ahead of time compilation option. And we are going to measure all of these 4 together to be able to compare between them and see which one of them has the biggest benefit for us. If we go to the makefile again, then we find all of these options here, and we will use all of them. But now let's first start filling out our table by making all the measurements that we need so that we can discuss this afterwards. The first option that we are running is just a simple boot application with no extra elements to it, except having the diagnostic options in the native memory summary available for us. And that is via this command run. So the first thing we want to do is compile our application, and for that we can just do a make run. And we just have to wait until it completes. It doesn't take long, and we've got already now our jar available in our build libs folder. And for that, to run it, we only need to run with make run. And there, we've got our application running. We see that it has started in 930 milliseconds, and that is what we're going to put over here, 930 milliseconds. Let's see now how much committed memory it is using. And for that, we can go to another tab, and right over here, we have the list of the different verify commands, just as much as we have seen in the simple Java application. They are the same, but they are separated here between 2 because the normal Java application is running in the build libs, or better said, it's running from the build libs folder, and the other one will be running from another folder after we unpack it. And therefore, that's why we need the separation, because we need to access the jar that is the one that's running. Therefore, the first thing we are going to do is to make verify native memory. And this is going to tell us somewhere over here the shared class space. And we are seeing that we get this number, almost 13 megabytes. And let's put that one over here. And we can already see that it has exactly the same value as a Java application. Why would it be the same value? That is something that I'll explain later when we get the results of running all the other types of applications. But for now, let's check on how many classes have been loaded with the Spring application running normally, like we usually run Spring Boot applications. So in this case, let's go to the command line again and do a make verify class loading. And right over here, we see that the total number of classes that have been loaded in this case is 9,209. And that's the number that we are filling in over here, right here. The total classes without CDS for the packed version. That is 9,209. All right, so we have our first data for the simple Spring Boot application. Let's now create our first unpacked version. And for that, we can run this script, which is the extract script over here. Then if we just say make CDS extract, it now creates an extracted folder of our Spring Boot application. We can have a look at it right over here. If we see the project folders, and if we go inside the validation company here once again, because that's what we just did, we've extracted everything to this folder, the validation company folder, and inside of it we've got lib, which contains all the necessary libraries to run this application, and next to it we have the validation company jar. If we run this jar, it means that we are running an uncompacted version. It means that it's open to run. And there in the validation company, we have our application. So for that, we can run another command that I have available in the make file. And this is the run unpacked. And again, with the same flags on, we will need them all the time to be able to assess these different properties of our running application. And for that, let's just run unpacked at this point. Let's stop the previous application and just run make run unpacked. And as we start to make run unpacked, we can see already one added benefit of simply just running the application without being packed. And that is the package where it resides with all the other external folders makes the application startup a bit slower. Not too slower in this case, but it really depends on what kind of application are you using. So if we write this down over here, where we've got the startup unpacked field, we can see already that we've got a difference of about 100 milliseconds. 100 milliseconds for this application that still doesn't have a database connection. It is quite significant because it means that with this limited amount of external jars, we are able already to save 100 milliseconds, and that can mean a lot in terms of running these services in the cloud, or if you on-premise or in your own home, let's say. So this is very important. Let's now see what committed memory are we using now. Is it any different? What do you think it will be? Let's see if it is different. Let's run again the memory makefile command, verify native memory. But now we are running this inside a package, and therefore we need the other command, which is cds verify memory. And this one we can see over here. So if we were going to verify the memory of our simple running application, our jar is then located over here. But our new jar, as we have seen before, is right over here in the test validation company / the validation company jar, which is what we can find over here. So we can now run this command and see how much memory is it using. And as we go here up, we can see already the shared class space, and we can see that, hey, there doesn't appear to be any change. Let's write that down. Over here, the unpacked version is not that different in this case. So in terms of memory, there doesn't seem to be any gain in having unpacked it. Let's see now what will happen to the total number of classes loaded. Is there any difference? You probably already know the answer to this question, but let's see it anyways. Let's run make CDS verify class loading. So we can see that the number seems to be different. Let's put that down on our table, and exactly, it is different. It seems to have loaded less classes. We will see later on where could this be coming from. For now, let's stop our application and make the first run into CDS. As we have seen before, after we extract our package, we can then apply CDS to it. And how do we apply CDS to it? By creating a Java shared archive file. And for that, we can just run the script that I created for it, and it is located right over here, this one. And what it does, it will run the application, and it will make use of this particular switch, which means that on refresh, the application will exit. If you remember from the previous case when we were using the simple application, we had a problem, at least I told you of a problem, where if we tried to get the class list, the application would go through it, and the application would start, and then CDS would try to make a list, but the application needs to stop. And if there is no way the application will stop, it will just hang indefinitely, not giving us the list that we need. So that's why I had created the keep flag for it. In this case, what we are doing is letting Spring know that once the first refresh occurs, the application will stop, and then we get the class list. This happens under the hood, and we don't get to see the class list that it generates. It does automatically creates the Java shared archive file for us. And that's what we get over here with this command. And of course, we need to give in also the switch for the jar to start. So let's do this, and let's make sure that we've got our Java shared archive file. Let's run make CDS archive. It started the application, and it has stopped it immediately. Now we've got right over here in the root folder of our module, the application.jsa file. That means that we are ready to start our application. So if we go to right over here, we've got the launch, and this launch command will start our application from the jar that is created after having unpacked it, and then run with the diagnostic and memory properties, and then run with the JSA file over here. Let's just start it. Make CDS launch. The application has just started, and we can see already a drastic reduction in startup time. Let's go to our table and register this one, which is really important. So with CDS, we were able to start our application in 430 milliseconds, which is a half of the time that we have seen before, packed or unpacked. What would that mean in terms of committed memory for the shared class space? Let's see. Let's run make CDS verify and then memory, native memory. If we go here to the shared space piece, we can see that the committed memory is now different. And if we write this here down, we can then compare it. We can see that the memory is substantially bigger, although substantially in this case is a bit of a rough word, because 55, it is about 3-4 times more, but we are still operating in the scale of megabytes, which isn't that significant for an application in current times. So this isn't a really big negative side to it. It doesn't really matter. It is very much insignificant for our running application. Let's now see how many classes it has used. And here we might also get a surprise. Let's see if we do. Make CDS verify class loader. Class loading. Verify class loading. We now have, in total, 8,975 classes loaded. So what does this mean? It means that we have loaded less classes, we are occupying more space. This means that there are more space being used when we are trying to load JSA files. It feels a bit contradictory to what we saw in the Simple Java application. There is a point here to be made. When we use CDS, it will combine what's in the JDK and what we give it for our application. It combines CDS and applciations together, and it will optimize that. How it turns out in terms of memory usage is unpredictable. It can lower it, as we have seen here before, but it can also raise it, as we see over here. And that has to do with the difference in class usage between the JDK and any extra that we use on top of it. In this case, we are using external libraries from Spring. And so naturally, the shared space will increase because the JSA file will include much more optimizations. Whereas in the case of a simple Java application, it doesn't use any external libraries. So that means that it shares a lot with the JDK itself, leading to potentially a reduction in the usage of committed shared space. Our last example is the ahead of time compilation example. And that one really works in the same way as this one, but there is a small difference, something that we need to do. In the build Gradle KTS, I've got this commented out. This is commenting the plugin that is necessary to perform AOT operations on our Spring application. I don't have anything special in my application that doesn't allow the usage of AOT, but we need to be aware that there are some limitations. And if we go to the Spring website about this, we will find some limitations to it. But those limitations are more relevant for maybe bigger applications, more complex applications, not for this one. So for this one, there was no problem. I could use it directly. And with AOT, that means also that when we start our service, we need to activate it. And if you have noticed before, the CDS startup was done by having the AOT flag disabled. So the spring.aot.enabled was set to false, so that we didn't took into account any kind of AOT optimization. It is set to false by default, so we don't really need to worry about it too much. But in this case we do, because now we want explicitly to activate it. But because I have also changed the plugin, and because I have now removed the comments, that means that we need to rebuild our application. And for that, let's just do a make, as we have seen before, and this make command I've also programmed to remove everything, to clean everything up. So we start fresh again, and it's also logically understandable that we need to stop the running application at this point. And now that the application has been compiled again with AOT, let's start it and see what happens. And to start our application, we need to launch it with a different command. So the different command is this one, launch CDS AOT, and this one is an improvement or another version, let's say it that way, another version of CDS launch that contains Spring AOT enabled, and this time with true value. It is the same thing we did when we created the archive, the JSA archive, and therefore we are now activating AOT in our application. Let's start it. and see what happens. Make launch AOT with the CDS prefix. So the application has just started, and we can immediately see one thing. I hope you have seen that too, that the application startup is much, much lower. We have gone from almost 1 second to about 300 milliseconds, which is an incredible reduction of startup times. Let's just add that to our table. The README file is here, so right over here, let's add it up. So we've been having an incremental reduction of the startup time. This is already great, and this is very important for us. Let's see if by any chance there's a difference between the committed memory of the shared space in the previous runtime with this one. So in this command line, let's just run the verify command for, in this case, memory. Make CDS verify native memory. And in the shared space, we find a similar result to before, and that is 53, just around almost 54 megabytes. And it looks like a very small reduction in shared class space. This reduction, of course, it is fairly random, but it has to do also with what AOT does. By optimizing, it can potentially mean that less classes are needed. In any case, let's continue and find out the total classes of the runtime using AOT. And for that, we already know the command for that. We just call make, and then we do CDS, and then after CDS we do a verify, and then we call class loading. And over here we can find that our CDS application with AOT activated has loaded a total of 8,704 classes, which matches with what I just mentioned about the start of CDS with AOT and the committed memory needed for that. But the most striking figures are these ones over here. We're able we were just able to start our application in different modes. We were just able to start our different applications in different modes. We were able to measure different kinds of properties that they possess in terms of Spring also with AOT and also the packed and unpacked versions. And we've come up with very interesting figures. The most striking figure, of course, is the startup time. That's what we want. And before we delve into now what it means to say that the committed memory has a certain value and that the total classes have a certain value, an important reflection here is to see that the difference in committed memory for the shared class space and the total classes used is not that much. There isn't too much of a difference. But that small difference when it comes to the native class shared space usage is very insignificant if we want to draw decisive conclusions when it comes to the effects of using CDS in the overall memory uptake of our Spring Boot applications. What we have seen with the experiments in this video is that the one property that gets clearly affected by the usage of CDS is the startup times. And the startup times were different between our Java application and our Spring application. In the first example, with our Simple Java application, we measured a startup time of 23.11 milliseconds without using CDS. When we used CDS on it, we measured a startup time of 29.27 milliseconds. That is a difference of about 6 milliseconds, which isn't very representative of any benefit or, in this case, a problem. But when we did this with the Spring application, we then saw important differences, and these were differences that told us about the benefits about using CDS with Spring. In the first case, we started our Spring Boot application without CDS. And without CDS, it took 930 milliseconds to start, which is about 1 second. Then we tried to start our application in its unpacked version. It started then in 808 milliseconds, which was already an improvement. With CDS, we were able to halve that startup time to 430 milliseconds. And then we decided to go one step further and add AOT to our Spring Boot application. And then our startup time was about 300 milliseconds. In this case, 297 milliseconds to be very precise. With all the other figures, we couldn't take any substantial conclusion when it comes to is CDS better to use or worse? What we did find is that the native class shared space increases size with CDS, and quite significantly, which is this over here. These numbers over here represent that there has been a very gigantic spike in terms of native class shared space usage. But native class shared space usage does not necessarily translate to the overall uptake of memory, and it doesn't mean that the overall uptake of memory will increase with the usage of CDS. It only means that there are more classes that will avoid dynamic loading, and it will mean that these classes will be directly mapped to the native space, meaning that potentially there will be more heap space and there will be, in general, more resources available for our Java application. But generally, the great conclusion here is the combination with CDS and AOT, whenever it's possible to do, will very likely result in faster startup times. And this means that our problem has been solved, and our cats in our spaceship are very happy because they were able to start our services much faster. So what we did, we created an application startup for our microservices and serverless functions whenever applicable. We were also able to see the effects of using CDS on the native class shared space, and this was by using the command line using the J command, the Java command. One important aspect to keep in mind, we were not able to check out the total memory application consumption, and this is something that I will probably make another video about it, but keep this in mind that CDS can potentially also save a lot of memory usage. The problem with making tests here is that it needs a more complicated application to see clearly the benefits of using CDS, and that also means more complexity and perhaps a longer video. And so I will leave that for another video, not for now. Also important to know is that Project Leyden and build packs offer support to be used with CDS. These are other projects that will probably be also another theme for one of the coming videos. In real-world use cases, we can use CDS for Kubernetes. So if we are using pods, we can potentially reduce the cold startup time for Spring Boot applications in containers. Given that Spring Boot applications can start faster with CDS, that also means that they are good candidates to use in serverless. They can improve the function invocation times in environments like AWS Lambda. If you don't know, an AWS Lambda means Amazon Web Services Lambdas, which are functions essentially that we can run in an AWS environment, and we don't have to worry about the server, hence the name serverless. It's not the only kind, this is just to give an example. And we of course can use CDS with Spring Boot applications in a microservice infrastructure. We can optimize the startup for clustered services in distributed systems. Obviously, we can make our application start faster, and that means that our services and our clusters can be better optimized. And if we have to perform things like auto-scaling or update of different libraries, or if we want to do anything where the service needs to restart, CDS can be a good alternative to make sure that the downtime is as low as possible, or possibly even none. To use CDS, we should follow some best practices. There are a lot of them that we can find online, but these I think are the most important ones. We need to keep our archives updated. I am talking, of course, about the Java shared archives. These should be updated every time the application updates. The reason for that is that we need to have the best optimization as possible, and we also need to have our classes ready as much as possible to be able to be mapped directly to our native shared class space. And if we don't update our archive frequently enough, then there could be more classes coming in that probably aren't necessary to perform things like dynamic loading and that kind of thing. If we are using containerized applications, one important thing is to embed the shared archive in the container images for portability. This is important because if we just run the JVM in a container and we don't put our JSA file, then there will not be any CDS on it, and we won't be able to run it with our application CDS. Therefore, our app CDS will not be available. Finally, the conclusion. What are the key takeaways to this? CDS is a powerful tool to enhance JVM-based application performance. We have seen one aspect of this, and that is via startup times. We measured them and we saw that our application, especially the Spring Boot application, can significantly improve the startup time. Spring applications can significantly benefit from faster startups and lower memory usage. This is true. This is what we've tested in this presentation. And implementing app CDS is straightforward and highly impactful. We saw this as well, and with the combination of AOT, ahead of time compilation. We have seen examples of how CDS actually works. We have seen it in action. We have seen how can we improve our startup times. We realized that our startup times for the Simple Java application aren't that great, but they are amazing for Spring Boot applications. We've also discussed possible use cases and went a little bit through best practices and how to use this in our own environments, for our development and for our software engineering goals. CDS is something very interesting that we can use, but there can be a ton of questions surrounding it, especially how can we adapt it easily? How can we avoid, for example, the extract? Or can we avoid using extract? Can we avoid using extracting jars? What are the tools available? And can we make this more seamless? And do we have to use these switches all the time? Those are great questions, but those questions I want to answer in another video. Not this one, but I will gladly answer these questions in the comments, so feel free to do that. Please put your questions in the comments of this video, and I will do my best to answer them and to bring feedback back to you. These are the resources that I've used to create this video. Here you can find an extensive amount of information about CDS. I've also used this to create the examples for this video. Here is the source code in this repository, Spring Master Test Drives, on GitHub under my username J. Esperancinha. And you can find me also on different social media outlets: Threads, LinkedIn, YouTube, Blue Sky, Mastodon, GitHub, HackerNoon, Dev.to, and Medium. And especially don't forget to have a look at my webpage, where you can find different posts and other interesting things that you might not find in other outlets. And for now, let me thank you very much for reaching the end of this video. If you are here, congratulations. You are now able to start your own application and apply CDS to it. And you know the difference between AppCDS and CDS, the benefits of using it. And I'm sure that you will try to use CDS now on your own applications. So that was the video about Spring CDS. I hope you've enjoyed this video. I hope you've learned something from it. And of course, I want to see your comments, of course. Let me reiterate that. And give us a like. Don't forget to subscribe to this channel. 2025 is going to be a great year for JasperTech, I think. I hope that I will be able to make more long videos and more carefully curated videos like this one. I hope to see you in the next video. And until the next video, have a good one.
As a short disclaimer, I'd like to mention that I'm not associated or affiliated with any of the brands eventually shown, displayed, or mentioned in this video.